Yeah, so it is very nice to be here. I would like to thank you, the organizers, for inviting me. I'm sorry I can only be here for today, but sometimes that's just how it is. So today is your chance if you want to discuss, and feel free to ask questions anytime during this presentation. Okay, so the data that I will show has been acquired in collaboration with this group of very skilled and beautiful persons. If your name is on there, congratulations, and otherwise it could be, you never know. I have a short outline, quick review of the electronic structure theory. Then I'll go into formulation of calculations of interatomic exchange interactions, how we do it. I'll give you some numerical examples, move on from there to spin dynamics and what we do there. And hopefully I'll have some time to say something about a multiscale approach we have for magnetization dynamics. So starting from the very beginning, this is now how density functional theory tells us a way to calculate the many-body problem without actually solving a many-body problem. We translate into an effective one-electron problem. So here it is, the famous Kohn-Sham equation. So all the many-body effects that the solid has is baked into this effective potential, and then the trick is then to find the best possible. So operating on this Hamiltonian on one electron state, you get back an energy in the electron state itself, and then Felix Bloch wrote in his thesis work, 1928, the symmetric form of the wave function as we now all use. Here it is. So it has the plane wave component and a periodic component to it. This is a story that started in 1928. I'll come back to when it is about to end. But this means that all the things we calculated, as you know, has now a little subscript k on it, because that's now so a practical example of this then would be the band structure of BCC iron. The effective potential that I mentioned can have a difference for different strength for spin up and spin down electron states. That's what drives magnetism. And so here's an example of a magnetic material, one of the more basic ones. And here you have the band spaghetti. So me and many others had the hopes that these excitations now would be something that would reflect a true excitation of the material. A true dispersive quasi-particle state, but as you all know, that's not the case. And it's only with the invention of dynamic and mean field theory that these kind of calculations can reproduce electron states that have true quasi-particle excitations that you can compare to measurements done at, for instance, angular salt photo emission experiments. So the story started in 1928, and it was kind of close then, or at least achieved a major breakthrough in the 90s. So I think it's a long and fascinating story. But in terms of ground state properties, you don't have to worry about the fact that you can't compare these energy bands to measurements. The DFT tells you that cohesive properties and ground state properties are still available to you via the density functional. And in this particular case, if you're interested in magnetism, all you have to do is occupy a number of spin-up states up to a Fermi level, and occupy a number of spin-down states up to Fermi level, and then multiply with the G factor of 2, and then voila, you have a magnetic moment of BCC iron that agrees very well with experimental data. So this is thanks in part to Felix Bloch that gave us the shape of the wave function, this one here. He later on, after his thesis, he moved on to get the Nobel Prize in physics, not for this equation, but for nuclear magnetic imaging and connecting to the previous talk. Clever guy and did a lot of things. So if I now take some fairly innocent materials, then I can compare the theoretical calculated DFT calculated spin moments, and I can compare it to experimentally measured spin moments. And here's a list of the usual suspects: FCC nickel, HCP cobalt, BCC iron, gadolinium, iron to phosphorus. It's one of these materials that is used as a parent compound, at least for magnetocaloric applications. The list can be made long here, and if theory and experiment are in perfect agreement, all these dots should be on this straight line here, and they are, and that's often the case. There are many compounds and systems where that is the case, and to the extent that I don't think anyone would be so interested in seeing a whole list of systems that would be on this list or on this line. Maybe you would more, and so would I, be interested in to look at compounds and materials that are here and that are here, and one can start wondering why is it that they don't agree so well between experiment and theory. And I think all the materials we have listened to so far today, at least, do not follow on this line. There's somewhere here or somewhere here. This is the story for the spin moments for the most simple magnetic materials. I think we didn't do it, but I think if one were to do such a plot for orbital moments, even on a DFT level, it would not look very good. I think one would see discrepancies. So that's something I haven't thought about it, but that's something one can actually look at. Another thing that one then identifies from these kind of calculations is the intrinsic nature of magnetism, at least in one way. And so here I'm plotting the spin density for BCC iron for cut on the 001 plane, normal pointing towards you. And so you have iron nuclei here, and then you see that the red is now in intense magnetization density and blue is low, and so all the magnetism is localized around the nuclei. And so basically I can then draw a circle around a nuclei and integrate up the magnetization density and replace this information with this information I can start thinking about, and that's what we all do in an atomic magnetic moment. We don't think about the density. We kind of look at it. But if it comes from these kind of calculations, if this red blobby thing would be situated in the interstitial region for some reason, we would not think of magnetism in terms like this. We would have to think about it in some other way. Now this is drawn, all the little atomic moments as an arrow, a red and a white point pointing in some direction. They're all drawn to be ferromagnetically aligned. They don't have to be. Many materials are antiferromagnetic or spin spiral or spin liquids or whatever they are. And what is guaranteeing or governing that is the intraatomic exchange, the exchange between these two atoms or between this atom and that is now the next step in my presentation. And so this is something that Kasnelson and Liechtenstein and Antropov and co-workers worked out, and so I shouldn't be telling the story, but I do it anyway. So the principle in how to think about or how to do these calculations is to say, well, I'm interested in to find out what is the energy change of these two atoms, and it could be this guy and that guy, this guy and this guy, but now it's drawn, these two atoms. What is the energy change if I make a small rotation of those moments? And from the Heisenberg Hamiltonian, we all know what that looks like. It's SI scalar Sj times the constant. But from the electronic structure information, you can also ask yourself, what is the energy change that requires? And so that's a little bit of a trickier thing to do, but it was done by the people I mentioned. So they figured out from the electronic structure, from the DFT functional, what is the energy change that is associated to this rotation, and then one can compare that to what expression is for the Heisenberg Hamiltonian and get a closed expression for Heisenberg exchange parameters. So to make a long story short, that expression looks like following. So the Heisenberg Jij's exchange interaction between atom I and atom J is this integral here. There's a trace over all orbitals in the system. There's a local exchange interaction on site I of one iron atom, for instance, on site I, and another iron atom on site J. And then there's a Green's function that connects these two, one for spin up and one for spin down. Here's the expression for the exchange splitting, basically the splitting of electron states. and the Green's function is 1 over Z minus Hamiltonian between states. So key references for this one, all this fantastic work are these three primarily, and then we wrote together with Misha and Sasha and Attila Silva. Last year we published this review that we, to the best of our ability, went over this field, how to do it and give an examples and so on. So you find that in Reason 1 of Physics last year. So that looks now as follows. Here is an example of FCC nickel, the calculated exchange interactions as a function of distance in the lattice divided by the lattice parameter. So the nearest neighbor interaction is dominating, but in nickel as well as for all metals. The exchange interaction is not nearest neighbor only, it has a second nearest neighbor, third, and actually there's a tail of interactions that go all the way out here. And it continues. And asymptotically, this will turn into an RKKY-like interaction. Oxides, damped materials tend to have this one significant, and basically the rest you can forget about. Metals, that's never the case. So in metals, it's always a tail of interactions, at least when you look at these kind of calculations. You want to test, of course, if this makes any sense at all. And so we took these exchange interactions, put it onto Heisenberg spin-Hamiltonian and subjected that to regular elements of statistical physics and calculated magnetic moment, normalized value, m over m0 versus temperature. And then we got this curve here. It's actually terrible at lower temperature, but it gives a fairly decent ordering temperature. This is for BCC iron, and so no matter what we do, Binder cumulant or specific heat, this one tells you that ordering temperature is around 1000 Kelvin. And that's close to the experimental value for for iron also. It comes out for innocent materials. This is a result that deviates from experiment maximum maybe with 10% or so. Our experience, and I know many of you also were. So with spin-orbit coupling, then this expression is the same, but it's also different. Here now we have spins on site I and spins on site J, but they're normalized to have magnitude 1. Sometimes our community does that. Maybe it's not always that helpful, but it's done. So that means that the size of the magnetic moment here is baked into this J here now. So that's in here somewhere. But with spin-orbit coupling, then this Heisenberg exchange parameter, which in my previous slide was just a parameter, some scalar value, now becomes of a matrix form, and so it has this generalized matrix form, and it has off-diagonal components that have both a symmetric part and an antisymmetric part. Off-diagonal components here have different sign when I go from this side to that side, and this is now the Dzyaloshinskii-Moriya interaction that gives us spiralization and things like this. So the fact that it's spin orbit that drives these off-diagonal components, maybe intuitively you can think about it that it's spin orbit that couples the spins to an underlying lattice. That's how the system knows that there are orientational preferences around that would drive them these off-diagonal components. Typically, these are much smaller than the diagonal ones. So Heisenberg typically dominates. But in some cases, the DM interaction can be of the order of 10% of the J's. If one now were to use this Hamiltonian, calculated this one, it is in principle possible to calculate the Kitaev exchange that we have heard about. To my knowledge, but I haven't followed it so closely, but to my knowledge, doing these kind of calculations, I don't think there are so many examples of systems that we have calculated, our community has calculated, where we say, fantastic, we have found a Kitaev. Calculations show there is a Kitaev system. I know of no example. I'm looking at the people that should know. So I don't think, I am also a little skeptical. That's what I'm carefully trying to say. Anyway, so this is now the generalization of the formula of the Lichtenstein-Kasnelson-Ansbov-Gubanov equation. You can also do that. There's another generalization in terms of including the effect of self-energy if you're interested in dynamic and mean field theory calculations and stuff like that. That equation is here. My talk is not about dynamic and mean field theory. I may make one comment on this. So again, we wanted to test ourselves and see how well we could calculate stuff. And so here's an example. We found we're not super interested in manganese and tungsten 0001 systems, but it was a good system that had been measured, and we wanted to test and see how well this. And so we calculated the dm vector for D1 and D2. Here's the size of this guy is blown up with a factor of 10, and D1 and D2 are now in these orientations. And so these are our results. I'm going to come to a comparison to experimental data on the next slide. And so this DM induced moment then can give rise to a spin spiral state. And here is a picture of what that spin spiral state looks like from our calculations. And here is a picture of what that spin spiral state looks like from experiment. It has this cycloidal spin spiral configuration measured with STM. And so the shape of this guy here, you see that has this D-shaped form here. D-shaped form here and here. And so we then also compared the periodicity of this magnetic texture compared to the periodicity of experimental texture. And that comes in the next slide. The experimental spin spiral wavelength was 2.2 nanometers, and we did it with just regular LSDA, 2.9. And then we did flex, dynamic and mean field theory with flex as an impurity solver. So that's the weakest form of taking dynamical correlations into account in these kind of calculations. It reduced a little bit, but we still have a ways to go, but it's not, it's kind of and so this was now a test that the whole machinery works, the equations make sense, and so on, and it was kind of a good comparison. So my next item of my presentation is then dynamics, and if you have a spin Hamiltonian, you can subject it to equations of motion, so let the spins evolve in time. We have the strength of the exchange interactions, and so that should be a possibility to do, and that's what you'll see in a second. But before I do that, let me remind you that the time scale of a magnetic phenomena that the field of physics are aware of is actually quite staggering. So the longest time scales that we have on our planet is the geomagnetic reversal. The Earth's magnetic field. Stefan, I'll give it to you. Don't take a picture. Yeah, you'll have it. So the Earth's magnetic field, it changes its direction every 100,000 to 1 million years. Very complicated phenomenon. It's not a trivial one at all. So 10 to the power of 12 seconds or so, that's a real slow one. And then the fastest that we know is maybe last year's Nobel Prize in Physics, attosecond time effects, and maybe more commonly for the magnetic community is the femtosecond. So this is now 30 orders of magnitude in times that magnetic phenomena have been identified and studied. And in between here, you have the AC transformer, you have lifetime magnetic data recording media, stuff like that. Once gave a talk like this and said, isn't it fantastic? And then some guy from the audience says, well, but you know, if you look at the time scale of the magnetic field changes in the galaxies, it's even slower than this. And so but this is on our planet at least. This is as slow as you can go. So now you know everything about the dynamics on the planet Earth. If you want to do simulations and calculations of that, you have to make a choice where on that scale you want to be, where on what lifetime you want to be. If you want to do the geomagnetic reversal 10 to the power 12 seconds, I don't think you want to pick up a time-dependent DFT code to study that. You want to do something else. And so you want to adapt your theory to whatever it is you want to study. And in the lab, in our world, there are basically 3 levels, I think, that are relevant. Micromagnetic simulations, then you can simulate experimental time periods that are really of the experimental nature and sizes of the simulation cell that covers basically the whole sample that was studied. So from that point of view, it is the best one. The fastest one that allows the fastest description of the dynamics is time-dependent DFT. Then you look at individual electron moments and electron states. So from that point of view, this is to be preferred. But then you have to do something that is much smaller in space and also shorter in time. I will focus on this one here in between, and then I'll give you some examples of what you can learn from that, and so you come back to this atomic picture of magnetic moments. And we'll see how that evolves in time then. So the equations of motions, again, I come to the Russian mafia here with Antropov and collaborators. It was derived 96, and so the equation of moment for an atomic moment at site I follows the Lambda-Lifshitz-Gilbert form. Maybe it's not so surprising that it should do that. This is what it does also for the micromagnetic model. Gamma is the geomagnetic ratio. Here we have a precessional term that is easily derivable, as you can see in this equation in this paper here. And then there's a damping term that is a little bit more tricky to derive from first principles. And this now really corresponds to dissipation mechanisms that are a little bit difficult to analyze from first principles footing from day one. So it involves all kinds of effects: electron hole coupling, thin lattice coupling, microwave radiation, anything you want. And so this is now a phenomenological addition to this equation. But if you look at this, then you'll see that suppose I have now a magnetic field, a Weiss field BI, and that has turquoise arrow pointing up, and I have a magnetic moment M sub I, and that's this brown arrow pointing this way. If I look at how the time evolution, how this arrow then, in the presence of this field, how it changes in time, it has a precessional term. If this is the only one, then it would live on a cone its entire life, and nothing would ever happen. Energy and angular momentum would never dissipate in or out of the system, and you would never reach a ground state or lowest energy state. The damping term does provide that, and that is now a term that has gives a torque that drives this moment in towards finding the local minimum. That's what it does. You calculate everything here. My third slide, I think, was the comparison of this guy calculated from first principles compared to experimental value. The B field here, you calculate from this expression here, a general expression where this could now be, if you want, the Heisenberg-Hamiltonian. And as you remember, we calculate everything in the Heisenberg-Hamiltonian. Here we have, again, the B field. Heisenberg exchanges here. But if you want to, you can add the dipole interaction, magnetic crystalline anisotropy, Dzyaloshinskii-Moriya, Zeeman term. Temperature enters these equations in the form of Langevin dynamics, and so that means that you have a little stochastic field of Gaussian form. B averages out to zero, but it can fluctuate and a little bit, pushing on the moment in different direction, and that is proportional to the temperature that the system is in. So you end up with this general if I now take an example like hexagonal close-packed gadolinium, it has a ordering temperature of 292 Kelvin. The exchange interactions that we calculate from the LCAG formula, it looks like this. And again, It's not nearest neighbor interaction only. It has always a little bit of a tail, and again it goes into an RKKY interaction asymptotically. It has some terms that are paramagnetic. That's good because this is a paramagnetic material, but there's also some interactions that are actually quite pronounced antiparamagnetic. You would not be able to guess this from experimental data. At least I don't think so. You have to do the calculation to conclude that this is now an antiparamagnetic interaction in the third and in the fourth nearest neighbor interaction. So how do I know if this is true at all? How can I conclude and get the feeling if this is reasonable? One is the calculation of the Curie temperature, just like I showed for FCC nickel, comes out in good agreement with measurement. Another one is, of course, magnons and the magnon excitation spectrum. So we took these JIJs, these exchange parameters, and the calculated moments of gadolinium, 7.6 μeV per atom, set up a big simulation cell and let those spins evolve in time as a function of temperature. And then after the spin, so this now involves hundreds or millions of spins in a simulation. Then after a while, when the spins had come to an equilibrium at some temperature, we started to do the measurement step of that, calculating the spin-spin correlation function, from which one can calculate the dynamical structure factor, S of Q and omega. Whenever that has a peak, you expect a magnon or a collective mode. And so that would be one way to compare calculations to experiment, and this is what it looks like. There are magnons measurements and calculations. The theory is the red curve here. Experimental data are the diamonds or whatever they are. And so it's kind of okay. We miss a little bit, but I think every theory should miss the experiment with a little bit. Otherwise, it looks suspicious. But we were kind of happy with this. And so if the exchange interactions had not been described properly in this calculation, we would not get this. If the equations of motions for the spin dynamics had been wrong somehow, we would not have gotten this. We would not have gotten the correct spin-spin correlation from the S of Q and omega. So it's a good test to see that things are working. I'm coming to an end. How much? I don't know exactly. We were screwed up.
3 minutes.
Yeah, good. So that's good. And I'll have a chance to show you a movie and for that. So sometimes you choose this one, sometimes you choose this one, but every once in a while you want to choose this one, but include somehow the effect of the atomistic thing, and then that's when you want to do multiscale dynamics. And so we are far from finishing this project, but we're working on it. And so the basic idea is that you have a simulation cell where you say, I don't care so much about what happens in this regime here. Here's the domain with spin are pointing up. Here's the domain with spins are pointing down. I want to do a simulation of a rather large body of material, so I do micromagnetic there. But look, I am a little bit interested in here because I suspect there's a local perturbation here. There's a vacancy or there's a defect here, and so I'd like to see what that does to the dynamics. And then a multiscale approach is maybe the best way to do it. And so here is snapshots of the simulation, how that goes then. So at some time the domain wall is here. It enters the atomistic region, which is this gray squared. As you enter this local region with anisotropy is scaled up with a factor of 10 compared to the rest of the material. This domain wall bends, and then it does things. And after it has left it, it's back into a straight shape. We did a couple of tests, more of this. Here is a picture of just an equilibrium configuration of domains, where they have atomistic in here and micromagnetic in here, and there's a handshake region in here. And if the handshake region shakes hand very well, then nothing much is changing as you go from one to the other, and that seems to be kind of okay here. But I would say this is of course, as you realize, this is now the heart of this problem, to make a handshake region that works as well as possible. And we have one version of it, but I don't think we have the best version of it. Okay, I'm gonna come to an end here by thought I would show you a movie, but. They were looking at it. So here's now, this is my final slide. So this is now a skyrmion that comes in the micromagnetic regime. So here's the micromagnetic regime, have that here. Here's the atomistic regime. Here's the micromagnetic regime on the other side. There's a small defect there, a line defect, where we have taken away one atomic plane. So there's just a dislocation and this skyrmion now, now, this is not a skyrmion for a particular material. We're just playing around with parameters. It is generated by an appropriate choice of D and J, and that's it. But you'll see now this, this skyrmion will interact with this defect. It will modify its motion. It's pushed from left to right by spin transfer torque, and so that's why it's moving from left to right. And it's going to feel this defect in the middle here. In this case, it's going to wobble around a little bit and then keep on going. But in some cases, we got this guy to go to the end and then turn around and come back and kind of sail up against the wind. This one doesn't do it. It's going to keep on going. But things like this is something you can do if you have a multiscale capability. So this is now a two-dimensional example. We're trying to work on better handshake regions, more generalized impurity steps in this. Work in progress, but we're having kind of fun with that. I am going to say thank you for your attention by showing you some of the reference of the things we have worked on. So thank you very much.
Thank you very much.